My name is Elizabeth Hill. I'm a mathematics graduate student from Kansas State University, and today I'm going to talk about computational efficiency of Hamiltonian Monte Carlo for genomic prediction. This study was done alongside two other math grad students from Kansas State, Adriana Ortiz and Lauren White, and it's part of a larger project studying the relationship between the genotype and phenotype of wheat plants. This is being led by Dr. Stephen Welch, Dr. Nora Bello, Dr. Nathan Allman, and Dr. Philip Allerman. I would like to begin by introducing genomic prediction and the model that we're looking at. Simply put, genomic prediction is the process of trying to create a mathematical relationship between the genotype and phenotype of an organism. In our case, we're interested in creating a linear model that describes wheat grain yield. The genotypic information in this model is represented by Xij, that's going to be the allelic frequency. And what we're trying to fit for this model is going to be the marker effects, beta j, an intercept mu, and a noise term epsilon that we assume to be normally distributed. Now this model is posed in a Bayesian framework, meaning that our marker effects are going to come from a distribution. And depending on what kind of distribution we use, we assume a different genetic architecture for our plants. A lot of times you'll see a normal distribution used, which corresponds to the ridge regression model. We're also going to look at two other distributions today, the student t distribution and the exponential distribution, or the Bayes A and Bayesian lasso models, respectively. These two particular distributions are nice to work with in addition to the normal distribution because they have heavier tails than the normal distribution does. And what this does is it allows for the marker effects beta j to depart from zero at a greater frequency. In order to fit this Bayesian model that we're working with, we have a couple of different algorithms for estimating our parameters. We have the first one we're looking at today is going to be traditional Markov chain Monte Carlo with Gibbs sampling, or I'm just going to denote it as MCMC for the remainder of the presentation. And then the other is Hamiltonian Monte Carlo, which has a sampler that's guided by some ideas from differential geometry. Now, traditional MCMC with Gibbs sampling tends to do really poorly for parameter spaces that have high curvature. This image right here is actually a really good example of this. This shows the joint posterior distribution for beta and its variance, sigma beta squared. As the variance gets closer and closer to zero, it creates this bottleneck effect because beta must also then become closer and closer to zero. And as the traditional MCMC sampler is wandering around in this particular parameter space, it has a really hard time sampling that inside of that funnel. And even if it actually does make it inside of the funnel, it has a really hard time getting back out. So you wind up with a rather inefficient and sometimes really biased sampling from that process. So as just to try to mitigate this, Hamiltonian Monte Carlo was proposed, and what it does is it kind of takes advantage of the natural curvature of your parameter space to get a more representative sample. It does this by combining the gradient with some momentum terms from conservational dynamics to focus in on what's called the typical set, which is the most representative portion of your distribution. This is because it kind of strikes a balance between the mode and then the tail of a given distribution. As a result, Hamiltonian Monte Carlo winds up with a much more efficient sampling process, and the samples that it gets are going to be much more representative. With this in mind, our objective for this study was to compare the computational efficiency of these two algorithms in the context of genomic prediction for wheat grain yield. The data that we used for this study, we had 2,400 different observations of wheat grain yield in 4 different environments that were provided by the International Maize and Wheat Improvement Center. Because it came from 4 different environments so that we could ignore the effects of these environments, the phenotype data was centered and scaled within each environment. As far as the genotypic information, the lines are homozygous and they were genotyped for about 1,300 different markers. And for the sake of computational efficiency, we centered the means, or we centered the allelic frequencies to the mean of each marker. This right here is the expression for the joint posterior distribution. Everything we're doing is within a Bayesian framework. So this is going to be a product of likelihoods and priors, where the priors are coming from these different models that we're looking at. So ridge regression assumes a normal prior for our marker effects, Bayes A assumes a student t, and Bayesian lasso assumes an exponential prior. Each one of these models also comes with its own hyperparameters that have to be estimated as well. So for example, ridge regression with that normal distribution, we have to determine the variance. So in the case of HMC, that's going to be determined using a half Cauchy distribution. And then in the case of MCMC with give sampling, it's going to be determined using an inverse chi-square distribution. For all the models, our two other parameters that we're looking at, the intercept and then the variance for the error term, they're actually all the same prior distributions for each model, although there are some differences in the priors depending on which algorithm you're looking at. I do want to take a moment and emphasize the difference in the study between the algorithms and the models that we work with. We are not comparing computational efficiency between the models, although there are some differences just due to the way that the hyperparameters have to be selected. What we are focused on is the algorithms HMC and traditional MCMC with give sampling, and each of those are going to be compared within each model. As far as actually implementing our algorithms, they were both run using R. HMC was implemented using a software called STAN, whereas traditional MCMC with give sampling was implemented using the software BGLR. They were both run for 3 chains with a length that kind of varied depending on how long it took to get 1,000 independent samples. The burn-in used was either 100 or 1,000, depending on what was needed to get convergence as determined with Gelman diagnostics. So some differences that arose between the softwares that we use. STAN came with a lot of options for fine-tuning the algorithm HMC, and also presented us with this option between a centered and a non-centered parameterization for our models. So this idea of centered versus non-centered parameterization arises from the fact that we're working with a hierarchical model that has parameters that are dependent on each other. So when we have a centered parameterization, that dependency is direct. So for example, with ridge regression, we sample our variance first, and then we sample the corresponding marker effects. But in the non-centered parameterization, there's a little bit of a more indirect dependency there. The variance is sampled, and then we have the scaling term ZJ that is sampled as well. And then our marker effects are determined based off of those. So STAN gave us the option of choosing between these 2 parameterizations, whereas BGLR only had the option of the centered parameterization. For HMC, we went ahead and tested both parameterizations. There are differences in computational efficiency. However, the numerical results for both of these wound up being exactly the same. So any numerical results you see from here out are going to be from the centered parameterization for HMC. As far as actually being able to compare our 2 algorithms and their performance, the first thing we wanted to check was to make sure that the numerical results agreed from these 2 algorithms. So we had to look at the joint posterior densities that these algorithms produce just to make sure that everything matched up. To actually measure the computational efficiency, we wanted to look at how many independent samples we were able to get and how quickly we were able to get them. So we took the effective sample size and divided it by the amount of runtime. So our measure of efficiency then is ESS per second. So here are some numerical results just to check to make sure that the 2 algorithms are agreeing with their estimations. These results are showing the posterior distributions for our intercept mu and the variance for the error term epsilon. And these particular estimations are coming from traditional MCMC with give sampling and the centered HMC. Like I said earlier, the centered HMC and the non-centered HMC produced identical results. They appear to agree more or less across the board. The only one that looks a little bit iffy is going to be the Bayes A with the variance. And if you look at the scale on that, it's really actually a minuscule difference. You're looking at hundredths and thousandths place. And it can be entirely attributed to the fact that they are sampling from different prior distributions. We can also measure how closely they agreed on our marker effects by looking at the genomic breeding values, which is what we're going to use to be able to rank the genetic merit of our organisms. And in this instance, we are plotting traditional MCMC along our y-axis and the centered HMC along our x-axis. And since our data points are aligned along the y=x axis, we see then that the 2 algorithms did agree in their estimations. So finally, here we have our computational efficiency results. They are organized by model, and within each model, we have each algorithm and its total burn-in that was used, the total iterations, the runtime, iterations per second, and then our actual metric of computational efficiency, ESS per second. Following that metric of effective sample size per second, we went ahead and ranked within each model. The best algorithm is highlighted in green and the worst is highlighted in red. We were really surprised to see that, contrary to what we had expected, Gibbs sampling, the traditional MCMC with Gibbs sampling did substantially better than the HMC algorithm did in either case. For example, if you look at ridge regression, it's really quite a bit better. You're looking at 5.2 ESS per second for the traditional MCMC with Gibbs sampling, as opposed to 0.06 for the HMC centered. It is, however, possible that this is just simply due to the computational complexity that goes into the HMC algorithm, because if you look at the total number of iterations, it is quite a bit less in each case than the number of iterations required for the traditional MCMC with Gibbs sampling. So what happened was each one of those iterations individually took a lot longer than any of the iterations from the Gibbs sampling. And so, like I said, that may just simply be due to the computational complexity of having to take a gradient and compute the momentum terms and all of that other stuff. So another thing that was really kind of unusual to see was Bayesian lasso. When you do a non-centered parameterization of it, you wind up introducing a lot of discontinuities into the parameter space. And since HMC operates based off of following the gradient around, combined with the momentum terms from conservational dynamics, it doesn't do very well when it has a discontinuity because it can't take the gradient there. And so those results have been really slow to produce. They're actually still in progress. So, but Bayesian lasso with the non-centered parameterization is highly inefficient. It's really just not a good option at all. So to kind of wrap this up, we did see overall consistent estimation of the posterior density of the parameters. So the numerical results matched from both of the algorithms that we were looking at. However, traditional MCMC with Gibbs sampling was more computationally efficient than that Hamiltonian Monte Carlo, which was surprising because Hamiltonian Monte Carlo is expected to get a more representative, more effective sampling than the traditional MCMC was. However, this is probably just simply due to the fact that taking a gradient is computationally intensive. And so HMC, each iteration, even though maybe it was more effective and more representative sample, it just took so much longer to compute it that it wound up ultimately being substantially slower. However, Stan did have a lot of options for fine-tuning the HMC algorithms, such as like setting the step size, mask matrix, jitter, all sorts of other stuff. And we're hoping that moving forward, maybe fine-tuning these parameters might kind of mitigate the slowness of computing all these different pieces that go into taking the samples with HMC. So that's going to be our next step in this work, is fine-tuning all of those algorithm settings for HMC. Finally, we just would like to thank our sponsors for this work, Kansas State University, Oklahoma State University, and the National Science Foundation. Without their support, this absolutely would not have been possible. If you'd like more information, here's some references for the talk and also some of the work that we've done. If you have questions about the project in general or just other things, please feel free to reach out to either myself or anybody on the research team. We'd be more than happy to talk to you. Other than that, that's everything that I have. So thank you so much for listening. I hope that you enjoy the rest of your day.